Recall that previously, as a corollary of Minkowski's convex body theorem, or more precisely, as a corollary of Minkowski's linear form theorem, we proved the following simultaneous Diophantine approximation theorem due to Dirichlet, which says, under some relatively mild condition, namely, if this matrix is irrational in some sense, namely when A is applied to any integer vector that is non-zero, you will always get a non-integer vector. If this condition holds, then we can find infinitely many integer vectors under some hypothesis such that the maximum norm of AQ minus P can be as small as we want. Now we would like to generalize this to the inhomogeneous setting. Namely, if we are given a vector B in Rm, can we have an analog of this result in this inhomogeneous setting? The theorem that we are going to talk about today, which is due to Kronecker, will generalize this result in some sense to the inhomogeneous simultaneous Diophantine approximation situation. So let's get started. Kronecker's theorem on inhomogeneous Diophantine approximation states as follows. Let A be an m by n real matrix, and let the vector B be a column vector with m components, namely B is in Rm. Then the following two statements are equivalent. First, for any epsilon greater than 0, there exists an integer vector P in Zm and an integer vector Q in Zn such that the maximum norm of the following vector AQ plus B minus P is less than epsilon. Notice that at this point we are just fixing a positive number epsilon, and look at the situation where the norm of this guy is bounded by epsilon rather than 1 over some power of Q. And notice that even this may not be true for any A and B. For example, so let me write this as a remark. The statement number 1 is not true for any matrix A and vector B. As an example, you just look at the situation when m and n are both equal to 1. And you take A just be a matrix with single entry 1, and B to be a vector with a single component 1/2. Then, if you look at this maximum norm, which in this case is just simply the absolute value, this is always greater or equal to 1/2, which cannot be less than the epsilon when epsilon is less than 1/2. So the statement 1 is not always true. And the really amazing part of Kronecker's theorem is that Kronecker discovered that the statement 1 is equivalent to the following statement: that if you have A transpose times the vector u is in Zn for some integer vector u in Zm, then you can always get u transpose times the vector b is an integer. So this is the whole statement. Although there's an implication in here, you should really regard this as a whole statement. Namely, whenever you have an integer vector u in Zm such that ATU is in Zn, then you have UTB is an integer. And Kronecker's theorem states that this statement is equivalent to the first statement. I know that when you first look at the statement 2, you always have an urge to simplify this a little bit. In particular, you want to remove this u. So you might wonder, can we simplify the statement 2 into another statement that only involves A and B? Some of you might be interested to know if the second statement is equivalent to just the following: whenever A is an integer valued matrix, you have the B is an integer valued vector. Some of you might wonder why the second statement is equivalent to this. Well, this is not true. Actually, you only get one-sided implication. You have this direction, but not this direction. This direction is obvious. If A is an integer valued matrix, then you just take U to be jth canonical basis vector in Zm, which means the jth component of U is 1 while other components are all equal to 0. Then it follows that ATU is always an integer vector. And it follows that the statement 2 will imply that EJT times B, which is really the jth component of B, is always an integer. So, in the end, you will get B is an integer vector. So, you will have the forward implication. However, the backward implication does not always hold. This is because if you just take A to be the matrix 2 by 2 matrix with all entries equal to 1/2. This is a symmetric matrix, which means it is equal to AT. And you take U to be the column vector 2, 2, which is in Z2. And you take the vector B to be the column vector whose entries are all equal to 1/3. Then the statement 2 fails. Why? Because in this situation, while the left-hand side holds, the right-hand side fails. Because for this particular U, UTB is not an integer. So the statement 2 fails. Now how about the right-hand side of this? Some of you might think, well, it seems that this also fails because B is not an integer vector. But you really have to look at the hypothesis in this situation. Notice that we also made the hypothesis of this fail by making A to be a matrix whose all entries are equal to 1/2. So the hypothesis is already failed. Simply by pure logic. By pure logic, if the hypothesis already fails, then this statement is always a true statement by pure logic. So, this part actually is true. This tells you that the right-hand side does not necessarily imply the left-hand side, namely the statement 2.